afternoon, so please join us in the conference area for the next and final session of our master workshop. Great. Good afternoon and welcome back. Thank you for joining us for this, the final session of our master workshop. We're going to be doing 3 presentations and then we will have a panel discussion led by Mr. Patrick McCory. The first session today is going to be a presentation by Alex Manuskin. He is a master student joining us from the Israel Institute of Technology, and he's going to be talking to us about Ostraka, a scalable blockchain node.
Thank you. So, hi, my name is Alex. I am a master student at the Technion. This is work done together with Itai Eyal. And today I'll be presenting Ostraka. This is how you build scalable blockchain nodes. So, in this talk I'll cover the scalability problem, present our solution, evaluation, and conclusions. Okay, so let's talk about the scalability problem. This is what we're all here for. Current blockchains don't scale well. And one of the reasons they don't scale well at the moment is a consensus problem. So a bunch of smart people got together, came up with many possible solutions for the consensus problem, whether it is Bitcoin NG that says let's decouple leader election from block creation, or some sort of BFT protocol that enables us to achieve consensus on many transactions fast. So while this happens, we are starting to see new bottlenecks. We still want nodes to be able to process, store, and propagate transactions across the network. So all of these can or will become bottlenecks in the future. So let's see what are the current solutions that are trying to mitigate these problems. So one of the solutions that you have heard of a lot about today during the sessions is sharding. So this is what sharding generally looks like. There are committees, nodes are being assigned to them. Each one of the committees is running its own sort of a subchain. Sometimes they need to interact with each other. And we get a higher throughput and nodes need to store less because each node only needs to be allocated to one of the shards. So there are plenty of examples that you have seen here today and we'll see later on. But these solutions have several limitations. First of all, shards can be brittle. Some people talked about it, that if the hashing power is split between the shards, one of the shards can be compromised. So now you're corrupting a single shard and by this way corrupting the whole network. Another challenge is the challenge of cross-shard transactions. The throughput increases. We would likely see more and more transactions that need to communicate between shards, and this becomes a performance problem as well. Another solution that is not the main topic of this workshop but should be mentioned as well is layer 2 solutions. So with layer 2, you open a payment channel or a state channel and communicate between 2 parties. Now, not all the transactions need to go on the blockchain, so overall throughput increases. Not everybody needs to hear everything, but layer 2 solutions have some limitations of their own. First of all, they are suitable mostly for long-term transactions, for micropayments. And if I want to buy a cup of coffee, I would still need to probably do a transaction on layer 1. And usually they require additional security assumptions. If, for example, you're using a Lightning Network, then you need to have some kind of deposit on the blockchain, and you can't use it for anything else while it's there, or a trusted execution environment. So our motivation. So we wanted to look at this problem. We said, okay, so let's say we want to keep the security properties of existing solutions. For example, resilience to 50% adversary. We want to, of course, increase the network's throughput. This is what we're all here for. And additional ideas are that most of the users can be using light clients, also has been mentioned here today. Many light clients that interact with full nodes, and people who have interest in running a full node, such as miners or exchanges or financial institutions, will have the finance to run a full node and the interest to validate the whole chain. So if this is what blockchains look like today, a single chain with small nodes running and validating the chain. This is the sharding solutions that are proposed, has been proposed, basically splitting the chain between shards and having small systems running on each one of them with the drawbacks and that we have mentioned. And what we are saying is, okay, let's run a single chain that's very secure, have big systems running the full nodes, but to make it more accessible, to keep it open and available, what we're going to do is shard the nodes themselves. Okay, so we're going to be using the term sharding, but we're not sharding the blockchain as in the classical way, or as others have talked about it, but we're going to be sharding the actual node. Okay, so this is where our solution comes in, Ostraka. So the meaning of the word Ostraka is shards of ancient pottery and clay vessels. Basically, we wanted a different word that means sharding, but okay, so the challenge is with building such a system, we need to split all the storage, need to split all the data structures that are needed to keep a blockchain. We want to split the validation effort, and we want to split the network bandwidth between the shards that we are building. Okay, so how are we going to do this? So each one of the nodes in this system will have some components, a coordinator and shards. So the coordinator connects to the network, orchestrates the P2P connections, talks to other nodes, and the shards, they are the workers. They store the blockchain and the UTXO set, they talk to each other if they need, and validate transactions. Now, all of these entities are part of a single node. Okay, there are no trust issues between the shards or between the shards and the coordinator. So it's not like one of them is trying to be malicious. How does it look like connected? Okay, so in this example, there are coordinator and 4 shards that you see. Each one of the shards is assigned a shard index by the coordinator when it connects to the node. And the shard index will indicate which part of the blockchain this shard needs to be responsible for. Okay, so shard 0 will be storing and validating all the transactions that, for example, start with 0. All the shards know all the other shards. They're all interconnected. So if a shard is missing some information, he knows who he needs to go to get this information. Okay, so how the two nodes connect to each other? Say node B has just joined the network. The coordinator of B talks to coordinator A. They exchange information. They understand who are the shards of each one of them, and the shards can now connect to each other. The number of shards in each node doesn't have to be the same, as long as they know exactly who they need to talk to, who they need to connect to. And in the whole network, you can be connected, of course, to more than one node, just like now, and we can run gossip protocols, etc. So let's look at how block validation works in such a system. Let's remind ourselves what a block in the UTXO set model looks like. So the block has a header, it has transactions, and this is a transaction. The transaction has a transaction hash. The hash is generated by a pseudo-random SHA-256 function and is evenly distributed. The transaction has outputs which tells us who and how much money they will want to pay, and it has inputs that reference previous transactions and the index of the output from the previous transaction that we actually want to spend. Okay, so let's say we have a system with 2 shards. So now, instead of each one of the shards storing the full block, each shard will store a block shard that will only have the transactions that are relevant to that shard according to the shard index, as we explained before. Great. Let's look at how a block would propagate in the network. So in this example, there are 2 nodes, Alice and Bob. Each one has 2 shards. And say node A has just found out or mined a new block. Oh, sorry. Yeah, okay. Sorry for that. Just at the crucial moment. Where do you plug this? Hmm?
This is the one?
Yes.
Which page?
Some more. No, go down. Yeah, this page. This. Okay. Sorry about that. Hardware is tough sometimes. Great. Okay, so we were at how does a block propagate in this network. So node A has just found out about a new block and wants to propagate it to node B. Okay, so coordinator A informs coordinator B that a new block has been found. Coordinator B informs his shards that a new block has been found. And now each one of the shards from node B contacts its appropriate shard from node A and requests the block shard that are relevant for this block. Node A, each one of the shards from node A send the appropriate block shard to node B, and now we'll look at how node B begins to process and validate these transactions. So let's look at node B. Okay, so node B has shard 0, shard 1. It has some inputs. And we said that the transaction hash is evenly distributed, so we would expect that in this case of 2 shards, about half of them won't be in the UTXO set of shard 0. If we have n shards, so n minus 1 over n of them won't be in shard 0, and he will have to request this information from shard 1. Now, he knows exactly who he needs to talk to get this information. So shard 0 requests the information, the signature, the script from shard 1. And if everything is okay, shard 1 sends this information. Now shard 0 has all the information he needs to validate the block and can continue validating the transaction in the next block. If there has been some kind of a problem with the block, if shard 1 does not have the UTXO, or it has already been spent, or if the signature is somehow invalid, each one of the shards can inform the coordinator that the block is invalid and disregard the block. So great, let's see if it works. So we've implemented it in Go. We forked it from forked in implementation of Bitcoin client written in Go because we wanted to see actual bottlenecks that we are running into and not just a simulation. We ran it on EC2. So in the following experiment, what we'll see is each one of the components will be this system of 2 cores and 4 gigabytes of RAM. Not too big, but this is what we want. So in the experiment, there will be 2 nodes talking to each other. Each one of them, of the shards and the coordinator himself is a system, like I said. And what we are going to do is change the number of shards and see if we can get better performance. So first of all, we started off with a single shard, single coordinator. The shards talk to each other. This is quite similar to a system, a reference client that cannot scale out. What we see, obviously, as we increase the number of transactions in a block, each one of the transactions is about 250 bytes. The time to process the block grows, obviously. We need to validate the signatures, we need to access the data structures, and this takes time. Okay, so let's see how it looks like with 2 shards. Great, we are already getting some kind of an improvement. It takes less time to process the same number of transactions. And to evaluate how much do we benefit from adding more shards to such a node, what we wanted to look at is a certain time limit. We took 10 seconds and say how many transactions can a node of such a configuration process in 10 seconds. The idea is if we want to keep the system secure, to keep the number of forks low, we want each one of the nodes to be able to process enough transactions fast. This is how we can increase the throughput of the whole network. So we took 10 seconds. This number can be changed according to parameters of the network, time between blocks and block sizes, etc. So continue testing this with up to 8 shards in this experiment. And what we wanted to look at again is basically where does the line of 10 seconds intersect each one of these lines to know how many transactions can a node process in 10 seconds. So these are the results. You see 3 lines here. Okay. First of all, there is the reference client that we were using. Obviously, it cannot scale out. We cannot just tell it, okay, process more transactions now. Its capacity is what it's got with given hardware. The blue line, that's Ostraka. This is basically, again, how many transactions this node can process in 10 seconds. And happily, we can see as we add more shards to such a node, it can process more transactions. The green line is the optimum. Basically, what would happen if we took the reference client, somehow automatically tell it, now you are 2 nodes, and there would be no overhead of running an inter-shard protocol. So the differences are about, for a system with a single shard, we get a difference of about 8%. We can process 8% less transactions. And this makes sense. We have additional protocol overhead. For 2 and more shards in this experiment, the overhead is slightly bigger, about 12, but it stays constant as we increase the number of shards. And obviously now we have inter-shard communication as well, so some additional overhead will have to be paid. Okay, so let's conclude. We wanted to build a system that keeps the security properties of existing solutions. We say, okay, let's look at sharding a bit differently, not by sharding the blockchain itself, but by making it possible to build nodes that can scale out as the network throughput demands it. So we are not telling everyone, let's replace your hardware, but you can add more hardware and still be able to process as many transactions as you need. This solution basically utilizes the properties, the nice properties of the UTXO set that can be very parallel, and we can be applied to other solutions as well if you need to build scalable nodes for that. So this is still a work in progress. There is an implementation and a paper in the works, but it will be coming soon. We still have some more kinks to fix and some more features to add. So this is it. Thanks for the organizers for letting me have this talk. Thank you very much.
Great, thank you, Alex. That sounded really interesting. Do we have any questions from the audience? Yeah, we have a question right there at the back. If we have a microphone. Or, it's coming, yeah.
Hi. I wonder how does affect the fact that one of your shards doesn't having. So let me do it again. So if one of your shards doesn't have certain UTXOs in their set, how does affect the?
Again, I didn't hear you.
So if you have a shard that doesn't have some UTXOs in that set, right?
Yes.
And you're trying to validate those outputs.
Yes.
And they don't have it.
Right.
How will affect the system?
He asks the shards that does have it, because it knows its shard index and knows the transaction index.
All right.
So he knows exactly who he needs to access, gets the UTXO set from them, and validates it.
And all right.
Great. We've got a question over here, please.
Hi. Great presentation. Thank you. Forgive my newbiness, but I was wondering how and if it can recover from a critical mistake. So, say for example, one of the shards. So you have this coordinator and an A and a B. Cool. What if B fails for some reason?
Okay, so basically, yeah, each one of these systems can fail, like in every other system that we are looking at, and it will take time to recover, but each one can be connected to several other nodes, so one node that falls doesn't crash the network. You're still connected to other nodes, and you can get your information from them.
And so there's no data loss of that?
There is no data loss in the network. I mean, the shard will need to recover. He will need to come back online, ask what has happened while I was online, while I was offline, get the information that he's missing, and continue working.
Awesome, thank you.
Great. Were there any further questions? We've got a question over here. Maybe I'll bring the mic. That's fine.
Have you looked into like more than 8 shards?
Yeah, we've looked at more, like up to 60, but yeah, I mean, maybe at several hundreds it will start to slow down.
At several hundreds?
I guess I've run up to 60.
Okay, that's interesting. Yeah.
Great. So any further questions for Alex at this stage? We've got a question at the back there.
Sorry, could you maybe explain some more about the security model between the communication between the nodes? The security model, basically, with communication between the node and the controller?
So nodes, the separate nodes, they don't need to trust each other. They can send each other invalid blocks, and the receiving nodes needs to validate it. But the shards in the single node, they belong to the same person. They're the same entity. So there are no trust issues between them. There's no shard that will try to fool you that he has an unspent UTXO that has already been spent. Okay?
Thanks.
Excellent. Well, that was a great discussion. If there are no further questions, then we will move on to our next speaker. His name is Kazım Rifat Özilmaz. He is the founder of Monolithic and a PhD researcher at Boğaziçi University. And he's going to talk to us about scaling Bitcoin and the UTXO space.
Hi. It's going to be a follow-up discussion, I believe, because I'm using UTXOs to split in any case. This is a paper written by me, Harsh Patel, and Ankit Malik. And we are going to discuss scaling Bitcoin specifically. My name is Kazım. I'm a PhD student in Boğaziçi University. I mostly work on blockchain and IoT integration, also a bit of consensus protocols, and I'm also an entrepreneur. So today we are discussing on-chain scaling, but on-chain scaling is easy, right? If we make Bitcoin blocks 1 gigabyte, then we have no problem. We almost catch the transaction throughput of Visa. But we all know that that's not the case. We have to keep the network decentralized also. We have to take care of it. So if we look at it, the bandwidth requirements of running a full Bitcoin node is actually a bit high. It's 400 kilobit per second upload, and you need to have at least 700 kilobit per second in total bandwidth in order to achieve a maximum of 7 transactions per second. So if we think that, okay, Visa has 2,000 transactions per second, and in order to achieve that transaction throughput, we have to have 200 megabit per second connections, which is very high. So will the future of full node in the data center? And well, storage is like that. Bitcoin is at 190 gigabyte right now. It's growing over 1 gigabyte per week. And if we consider full blocks, full SegWit blocks, then it's going to increase 4 gigabytes per week. And it's also it's going to require a lot of storage in the future. So is there hope? I'm going to give you a quick summary. So what we are trying to achieve here is we want to create multiple blocks in the same block interval for Bitcoin by creating multiple subchains. And we are going to introduce another chain called eigenchain, which keeps track of the subchain headers. And we are also going to introduce a new type of Bitcoin node called half node, which enables a user to track a subchain and an eigenchain instead of getting all the blockchain block messages. So in order to do that, we have to look a bit deep into UTXOs. As you know, Bitcoin transactions are consisting of inputs and outputs. In order to make a transaction, you have to reference a previously sent money, a previously sent transaction to you. So currently, the first session of the previous day was talking heavily about UTXOs. So currently, there are 57 million UTXOs, and a good amount of them are dust right now. So basically, this is the implementation, right? There are 3 classes, and the most important class, in my opinion, is the CTX out, which is the transaction output. And the most important part there is script pubkey, which defines where we are sending our money. So these are the mostly widely used 2 types of script pubkey. These are the scripts, and pubkey hash, you see, is basically your address. And the script hash is also the hash of your script. And these 2 types of script pubkeys are consisting 90% of the total Bitcoin transactions. So, after that pre-knowledge, is there hope? So we divide the UTXO set by creating by calculating hashes of calculating the hash of the script pubkey. So if you have one address and you got a lot of transactions sent to that specific address, all the hash values of these transaction outputs will be the same. So we calculate hash values for all the unspent transactions, and then we are going to divide them. There are a couple of strategies to divide these UTXO hashes. You can start by accumulating the amount of Bitcoin, and if you reach the half of the Bitcoin in circulation, then you may say that this is the threshold. Before that will be the Bitcoin number 1, and after that will be the Bitcoin number 2. So we are effectively dividing the spendable money into two separate groups. And by doing that, we are actually dividing the chain state DB, which is the actual database that Bitcoin implementation uses to keep track of UTXOs. And also we are dividing mempool, which also listens, which is the pool of transactions that nodes receive. So every subchain will accept only a subset of UTXOs, only a subset of transactions, and we effectively have chain state 1 dB, chain state 2 dB, and mempool 1 and mempool 2. So throughput will be increased because in one block interval, now you are able to create multiple blocks, and they will not clash with each other. They don't have to query anything to each other because UTXOs are already separated. So you have an account on all the subchains, effectively also. No cross subchain transaction possible. We are going to revisit that. Let's say that it is now. So what is the mining going to look like? Well, we are not addressing mining pools. The mining will be relatively the same. The miners should create blocks for all the subchain plus one block for eigenchain, which should contain the hashes of these subchain blocks. So mining will be a monolithic big thing still. They have to calculate everything, and the eigenchain will actually encapsulate all the information, all the hash values of these specific subchain blocks. The actual difficulty level will be determined by the eigenchain. So there will be proof of work for subchain blocks, but it will be relatively very, very low. So what the network is going to look like? So now we are able to actually partition the network. So we have full nodes. Miners are also full nodes because they have to listen to all mempool messages, because they have to create subchain blocks for all the subchains. So full blocks are sending messages, complete block messages among each other. So they are sending the complete thing. But their subchain networks only receive the required subchain block plus eigenchain. So it's possible to actually conserve bandwidth there because full nodes are not going to send the whole block message there. And all the subchain networks are able to independently verify because they have a subset of UTXOs. So it's possible to work independently. The subchain nodes will relay messages to full nodes also. And one of the problems that is going to arise at this stage is if you don't have enough money in a specific subchain to send to another peer, but your total balance is very sufficient for it, you have to make multiple transactions on subchains. So in order to achieve that in a secure and successful manner, you have to use hash time lock contracts. So you have to create a data, have the hash of it, use that hash to send your transactions, and in the end, you're going to reveal the actual data to your merchant or to your peer, so he can able to cash out. And if all the transactions are not happening in a timely manner on all the subchains, then of course this money will be claimed by you again, so you are not going to lose anything. So this is one of the mechanisms that should be taken care of. But all these things can be taken care of by wallet implementations. So it can be relatively not transparent to user. So if we compare, we talked about Bitcoin NG a bit. So there is SegWit, there is this failed SegWit 2x, which is only block size increase. And there is Bitcoin NG. As said in Bitcoin NG, there are key blocks that miners introduce, and then there's a 10-second microblock interval. This leader the party that introduced the key block is able to create microblocks, which, as a result, increases the throughput very highly, but it doesn't help you conserve any bandwidth or storage. With split scale, in terms of miners, you have to do the whole mining. You are not allowed to mine a specific subchain in order to, of course, for security reasons. And basically, full nodes will receive the big blocks, so they are also unable to conserve anything. But the half nodes will only receive the specific subchain and the eigenchain, so their storage requirements will be relatively low. Of course, full nodes will store everything, like in regular Bitcoin. And the bandwidth requirements will also decrease for half nodes because they will be, they are only getting block dash and the specific subchain block messages. So they are able to conserve bandwidth, and they are able to safely check transactions, and they are able to make transactions in a secure manner. So to sum up, what we are trying to achieve is we want to increase the throughput by giving the option to create multiple blocks in the same block interval by separating the UTXO set. And this new type of Bitcoin node, half nodes, makes it possible to run in a bandwidth constrained environments. So thank you very much.
Thank you, Kazim. That was very interesting. Do we have any questions from the audience for Kazim? We have a question here. Great.
Hi, thanks for your talk. I was wondering, like, how to decide or to restrict miners to mine on all chains and not on specific chains.
The only the only option is just broadcasting the block message. If they don't broadcast the block message, they don't get anything.
But as an adversary, I can just like mine on one of the subchains.
Okay.
To do that,
and you have to also mine. You have to also create an eigenchain block, which is the actual difficulty. So you have to mine the eigenchain block also, not the only subchain.
Maybe some honest node mines that for me, and includes the reference to my chain. Like, I'm not getting how this works. So how do I pick the chain I mine, or what I can do as an adversary to select and selectively mine only particular chains?
If you selectively mine a particular chain, you have a header, block header for a chain. You don't have the other ones. Then you just fill it with garbage data, okay? Then the collective hash of these headers should be also lower than a difficulty value, which is the actual mining operation, actually. That's what you didn't do. So you are unable to broadcast a valid block message to the network. So you are unable to mine on a specific subchain, actually, because I can explain it.
Yeah. We take it offline. Yeah.
Yeah. The part is the eigenchain. Eigenchain stores the hash values of the subchain block headers. Okay, and this is the part. This is the difficulty thing. This is the actual proof of work there. So you have to create eigenchain block. All right. We'll talk. Okay.
Excellent. Were there any further questions at this stage? We have a question here.
Okay, no, man. you already know the old UTXO. Okay.
Yeah, I wanted to ask about how bad does the hash time lock transactions, how do they affect the throughput?
In terms of latency, or in
terms of you now need to have some kind of synchrony to make sure that you move the
Yes, the reason that we had to use hash time lock contract is we are not 100% sure whether these multiple transactions are mined. But hash time HTLCs gives us the capability that if they are not mined, for example, in a 10 block interval, I can claim back the money. I can get the money back. So, as a sender.
I'll ask you about that later. Okay,
it's not wasted, so it's not lost.
Were there any further questions for Kazim? If not, then we will go to our next speaker.
Thank you,
Kazim. So our next speaker is Pierre-Louis Roman. He is he's from the University of Rennes.
Yep.
And he's going to talk to us about Dietcoin, verifying Bitcoin on your smartphone.
Ja, dank u wel. Okay. So, yeah. Thank you for inviting me, first of all. It's been a fairly good weekend, so had lots of nice talks, and it's really nice to be able to participate at that kind of event. So, I'm not going to talk about throughput scalability, but more about bootstrap scalability and storage scalability. And just in a one-liner kind of fashion, what we do is a UTXO commitment, so like you've heard today several times. But because we change the structure of the commitment of the Merkle tree, we have it predictable. Then we can do full block verification and several full block verification. So we actually have a subchain verification. So, as said, I'm PhD in Rennes. I'm actually finishing in a month, so not PhD for not very long. I'm finishing exactly 30 days, and I essentially work on decentralized systems. I'm interested in the theory behind it, but I find it slightly harder, so I focus on what I can do in systems, essentially. What I'll talk about has been put into a research report, hasn't been published yet because we haven't finished the evaluation. The research report, my co-authors are from the FU here in Amsterdam, and Spiros, who used to be at the FU and now is in Athens. And just little footnote here, Dietcoin is not Diet Bitcoin. Has anyone heard of Diet Bitcoin? Yes, no? No. Just a few FYI, Diet Bitcoin has been created by the brother of Pablo Escobar, just for your knowledge. I have no idea what's going on in it, but it's just, the guy used to be the accountant of the cartel, so I don't know what's going on in it, but let's all be nice towards this Diet Bitcoin. I want to go home alive, so just... Yeah, so moving on. So you all know the basic properties of Bitcoin, and I'm going to focus on the trustlessness of it, and also on the scalability of it. The fact it's public is something novel, and all of it is possible thanks to the blockchain that has been done under Bitcoin. I like to approach things from an abstraction point of view. It helps me understand things. So if you try to abstract blockchains, you have a ledger object, a distributed ledger object, and it's essentially just an append-only queue of records. You can put transactions, you can put contracts, you can put whatever you want, but it's just a queue. And because you only have two operations, append and read, you cannot add record in the middle of the ledger, or you cannot modify records in the ledger. So that's why we have an infalsifiable ledger. Because the ledger is distributed, you need to have some form of consensus between all the participants. And when you look at blockchains, it's just essentially just an instance of a ledger. So the ledger would be the service, and the blockchain would be the implementation. It's often used for decentralized ledgers, typically for proof of work or proof of stake. And the way you do actually the modification, the infalsifiability is to have the chaining with the hashes in integrity with the proof of work. Every block is actually a commitment to the database. You have a database which is the UTXO set. I'll talk again later about it. And the blocks are just updates to the database. In particular, Bitcoin, so I said it's public and it's also secured thanks to proof of work. And the trustless part of it is because it's fully verifiable. You can verify both the chaining, the headers, and verify the content transactions. That's what I'm going to focus on today. And the append operation is just by blocks, and it's done by miners, so just a very small subset of people. So about transactions, the validity of transaction, you have very few rules, basic rules, same in real life. So you cannot spend money that doesn't exist. You cannot spend money that you don't have actually, isn't available, has been spent already, and you can only spend money that you have yourself. You cannot create money either. So just 4 simple rules that are verified, enforced every time you have a new block created. I'm going to quickly go over it because it's been done already. So if you want to create a new transaction, you just reference previous outputs, essentially coins, and you make sure that they haven't been spent yet. So this one is valid. If you continue, this one also is valid because 1 and 5 haven't been spent yet. And if you continue again, this one will be invalid because 5 has been spent. So that's why nodes usually store the set of unspent transaction outputs. The transaction outputs being coins, unspent being available, so it's all the set of available coins. It's actually not the form in which it's presented in real life. You have them in blocks. So when you get a new block, you're going to verify all the transaction inputs that they are indeed in the UTXO set. So in this specific blocks, the block is valid because all inputs 1 is in the UTXO set. If you move forward, you can see that the next block also is valid because 2, 3, 4, 5 are also in the UTXO set, so it's valid. And the third block is trying to spend 1, which has been spent already, so it's invalid. And it's also trying to spend 9, which doesn't exist. So that's what the UTXO set is about. It's about the verifiability and the trustlessness of the system. So the verification process overall in Bitcoin, you first have to replicate the chain locally, so download all the chain, and you download all the headers first, and then transaction. The idea is that the headers are much smaller, so you can download them faster and check faster. The verification is based on simply agreed upon rules, so there is no consensus in between the systems, it's just agreed upon before. So you agree to the consensus from the moment you download Bitcoin and just you run it. One of the problems is that it's a sequential verification process. It's very linear, you cannot shortcut it. So if you want to start a Bitcoin core today, you're going to have to download 10 years of blocks and verify everything. So it's a real problem. And because it's very lengthy, you also have, we showed earlier that it was about 200 gigs of blockchain. So it's both time and bandwidth expensive. So full nodes have to download everything, check everything, which is very expensive, and you can't really do it on a smartphone. I don't want to blow my 3G connection, and if you think about countries in Africa that don't have strong infrastructure, for them it's a real problem. So you have another alternate mode, which is a light node. This is just 40 megabytes of headers to download and to verify. So this is actually doable on a 3-4G connection. However, you only verify part of it. You only verify the difficulty of the blocks without verifying their correctness. So existing light nodes, SPV nodes, make the assumption that because a block is difficult, it's also correct, which is not true. But they have to make the assumption based on the performance. And so when you look actually at the blockchain size and UTXO size, so the blockchain is in blue, UTXO in red, you can see that the blockchain is about reaching 200 gigs soon, about 1 gig per week. And the UTXO set is about soon to be 3. There is a big spike when they updated the way that they indexed all the UTXOs, and you can see another spike and going down when apparently Coinbase managed to regroup all of his UTXOs. So when you look at the graph, you can infer that in the future it's not going to get better, it's going to get worse and worse and worse. So it's better to have a solution now and prevent to have it in the future. So the problem is that light nodes don't verify the correctness of blocks, they just assume it. And if you want to build the UTXO set, it actually requires a lot of bandwidth and time. You cannot skip ahead. So the very simple problem that comes with it is that it's possible to have incorrect transaction in the block, although difficult. It's possible, and then a light node will be tricked with it. That's also why we have fraud proof that Mustafa presented earlier. It's one of the contributions. And the basic intuition is just to make the UTXO set queryable. So full nodes will have the UTXO set, and light nodes will just query it. And so our system, we call it diet node, just light nodes plus block verification, because we can verify all transactions. The bootstrap is much faster than a full node, obviously, because we do less verification. And compared to an SPV node, we have an improved security. The problem is that since we do more verification, we also consume more bandwidth, but we can't have everything. And again, that Byzantine guy, he's thinking, what if a diet node receives incorrect UTXOs? So the typical way of doing it is that you actually have UTXO commitment, you put the hash of UTXO in the blocks. which has been showed earlier. So the very basic idea, the strawman approach, is to put the hash of the entire UTXO in the blocks. So you have a new rule, you have a consensus rule on the validity of the UTXO set. So when full nodes receive it, they have to ensure it's correct. And the good thing is that it works. The problem is that if you have a smartphone, your light nodes still have to download the 3 gigabytes of UTXO set, and that's not really doable again on a 3G or 4G. So the next approach is to use a Merkle tree on top of the UTXO set. So that's the first time I saw it. It was a post by Andrew Miller in a Bitcoin talk. So he has since moved forward with more formal proposal to the community. And the good thing with it is that you have much more precise queries. You don't need to download the entire set, just what you need, and the partial Merkle tree to make sure it's included in the set. The problem is that you have a huge tree if you have actually a balanced tree, which is not always the case. But if you have a balanced tree, you have about 100 million hashes, so that's about 3 gigabytes of data. So on top of the already existing 3 gigabytes of UTXO set. So that's a big overhead. And you have lots of leaf insertion and deletions, so you need to have either a self-balancing tree or something like a sparse Merkle tree, but I'm not quite sure how much it would differentiate with the full node storage overhead here. And so actually our proposal is just to put UTXOs together. So because the tree is so huge, if we put the UTXOs together in shards, we're going to reduce its size in overhead. That's how we shard it. We don't shard the verification process, we just shard the state at each node. So the sharding here is done by using the first few bits of each UTXO hashes. And so you can see here, if you have a transaction, you want to know in which shard it should be, you just look at the first few bits. It will determine the shard. You have the policies, but I'll talk about that later. And so if we, in our setting, assuming a certain parameter m, we have a full node storage overhead of just about 1/4 gigabyte, which is much more acceptable than 3 gigabytes. And the bandwidth consumption to verify one node, it's really big cap, assuming you have up to 10,000 both inputs and outputs in a block, so 10,000 shards will have to be downloaded, each of average size of about 0.6 kilobyte, and you have the partial Merkle tree that's about 10 megabytes per block. The big M that I mentioned earlier, it's the one parameter of the system that we have to add into Bitcoin, is the cap on the average shard size. So with time, the shards will grow in size, and to make sure that actually they don't get too big and make it difficult for light nodes to download them, when the shard gets too big, we have to just split it in half, and that's what the M is. That's we make sure that shards on average never get above 1 kilobyte. The good thing with this approach is that you have a parameters trade-off, so K. You can just change K and you will have a different tree, a different overhead for full nodes, and a different bandwidth consumption for light nodes, diet nodes. And something that is actually new and I haven't seen in other UTXO commitment proposals is the fact that we have a predictable tree. So we don't do insertion deletions, we update shards in place. So the Merkle tree doesn't change its shape. And what it does is that it enables us to do subchain verification. I'll show an example in just a minute. And so what we do is that we actually link the UTXO set with the blocks. So you have the blocks with the update, UTXO set with the state, and we just put the Merkle root of each UTXO set in the previous block. So it's after the block has been modified. So you have a codependency that verify, modify in between the UTXO set and the blocks. So the nice part of the proposal is the subchain verification. So we have to trust a block, say 7 blocks ago in Bitcoin, if you want to verify 6 blocks. You trust a block 7 blocks ago, and you can verify all the next ones. It's a shift of trust from the Genesis block to a block that you want. That must be fairly recent, but 7 blocks ago is still okay. And what it does is that it effectively shortcuts the verification process. You can verify the subchain of the size you want. So about the example. Here we just have 3 blocks, and you're going to trust the one on the left, so we don't care about transactions. You just trust it because you're going to need the Merkle root of UTXO in it to verify the next one, to verify the next one. So the first thing you're going to do is that, as brainy as someone very suspicious, you're going to first apply the sharding policy to the block in the middle. So we replace 435 with the shards identifier they should be present in. You can do it because, again, you just look at the first few bits of the shard of UTXOs, and you can guess in which shard it should be in. Once you've identified that you actually need shard A and shard B, you're going to ask to a full node or a miner for shard A and B, and for the partial Merkle tree as well. The full node or miner is going to answer you back with just the shard that you want. It's green because it's identified to the block on the left. I'll use different colors for after. Once you've got all the shards in partial Merkle tree, you recompute locally the Merkle root of the tree you just got, and it should be equal to the one in the block. That's just the consensus. It's just to make sure that the shards you have are correct. So now that you have that, you can verify the block in the middle. So you're just going to check and update your shards according to the transaction inputs and outputs of the block in the middle. So you check the inputs and update with the outputs and inputs as well. So once you've done that, you have effectively verified the transaction in your block in the middle, and you have new state of shards. But you haven't verified the Merkle root in the middle, not yet. We can do it right after. So with your new state of shards, you can update the tree locally, and you should get the same Merkle root that the block in the middle. The reason for that is just it does the same job as a full node. It's just it does it on a very small subset of UTXOs. So you can do it locally with just a few kilobytes, a few megabytes actually. And once you verify that Merkle root in the block in the middle, you've fully verified the block in the middle, not just a full node would do. So a light node can do a full node job on a subchain of blocks. Then once you've done that, you can repeat the process, use the Merkle root in the block in the middle to verify the block on the right. So you repeat, apply sharding policy. You actually see that you actually need the shard C this time as well. You ask for shard C, ask for the partial Merkle tree again, get shard C, ensure the Merkle tree is still correct with the Merkle root that you have, and you're going to apply your shards to the block, checking the validity of transactions, updating your shards in the process, just like a full node would do. You've successfully verified the transaction in the block. You've updated your shards with the new state after the block. You can now update the Merkle root of the UTXO with a new set, with a new state, and you should have the same Merkle root as you have in the block thread. You can repeat, repeat, repeat. So that's a way I haven't found in other UTXO commitment proposals to actually be able to verify subchain of shards, subchain of blocks. So compared to being able to verify just one block, it's obviously much more difficult to counterfeit 3 blocks, 4 blocks, 6 blocks than just counterfeiting one. So diet nodes are much more resistant than nodes that only verify just one block. Oh yeah, no, he's very happy. Okay, smug. And so there is a problem actually with this approach, is that you have the parameter m that's set to 1 kilobyte. It can be a problem because it changes the entire tree. So the parameter is used to split all the shards when the average shard size is above 1 kilobyte. And when you split all the shards, you change the entire tree. And so you cannot have a predictable tree when you have that happening. It's just that in my example here, I have k equals 22. So it only happened 22 times in 10 years, so only once every 6 months, roughly. So it's actually okay, it's not that bad. You're just going not to be able to verify a subchain every few months, so it's okay. The evaluation, the goal of the evaluation is to actually to compute the bandwidth, storage, and the battery consumption of light nodes that will be run on a smartphone. The security will be just analyzed. The setup for the evaluation is that we want to have as best an evaluation as possible. So typically the question of dataset comes in mind, and with Bitcoin we have a public dataset, so we might as well just use it. So we're going to replay the public Bitcoin blockchain to a diet node. We're going to use popular code because we want to use a smartphone. We're going to use Bitcoin J and just have an application based on Bitcoin J. And the light node will actually be just on the smartphone, doing as minimum work as possible and doing all the complexity from in the server side, hiding it from the smartphone. Our scheme, from the point of view of the phone, of the diet node, it just sees a foreign full node, and it just follows the Dietcoin algorithm protocol. So you register like an SPV node would do, you get the headers, you get some of the blocks, and then you verify the blocks with the UTXO shards. That's what the diet node sees. But in reality, it's slightly more complicated, such as life. And so you actually have a replayer in the middle, and you have a Bitcoin core on the far right that is used as storage. So the replayer will just get the blocks one by one at the frequency that he wants. So let's say 1 every 10 seconds if you want to replay it fairly faster. It's going to send them back to the phone, and for the phone, it's just going to be completely oblivious. Just going to get blocks much faster than it should, but why not? Everything in red is something I had to modify in the BitConj library, so we almost finished with the code, not quite. I have the full node replayer, SPV node replayer, not just quite diet node. And this evaluation scheme can actually be reused for other protocol improvements that modify blocks. But typically, when people want to test their improvement, they test it on testnet or by creating blocks, not by using always the public available blockchain, which, in my opinion, it's a bit of a waste. It could be used. So that can be reused for other improvement proposals. So that's about it for my talk. In summary, I presented you diet coin and a diet nodes that can verify the correctness of transactions and then the correctness of subchain of blocks. You always have an overhead because you do more verification. You have an overhead for full nodes as well as for diet nodes. And for future work, first finish the evaluation. One nice thing is that we can actually use a DHT, then that would be the next step. Because we have shards of UTXO, we can put them on the DHT just like blocks. So then we can reduce by even more the storage footprint on each node. There are other sharding policies possible. You can use the script, for instance, but if you use the script as a sharding policy, you can get attacked much more easily. I mean, it's possible to spam much more easily than if you're using randomness. And lastly, it can also be combined with two completely different approaches. So I've proposed something that enables easier correctness, verification of correctness, whereas an IPOPO, so non-interactive proofs of proof of work, enable easier verification of difficulty. So we can combine the two together and probably have something even better than what we currently have. And lastly, a nice thing about Ethereum Casper, one of the many things it can do, that you have final blocks. So blocks that are old enough have strong consistency, so they're final. And since we do need a trusted block for verification process, we can use a final block as trusted and do the verification starting from there. So if you combine these two Ethereum Casper, you can actually have a full node with the same security guarantees as a full node verifying everything, but here just verifying the last few blocks starting from a final block in Ethereum. So can be combined with Ethereum, can be combined with Bitcoin, with pretty everything. So that's it for me. If you have questions, feel free. The slides are online, by the way, on my site, if you want. Okay.
Thank you, Pierre. I really enjoyed that. So do we have any questions for Pierre based on that talk? Well, I have a question for you, Pierre. So what do you think are the main challenges to implementing this kind of approach?
Convincing people to use it. It's always that, I mean, so I mentioned Bitcoin and Ethereum, and funnily enough, so from the outsider perspective, Bitcoin seems revolutionary. And when you're within it, it's a very conservative approach. It's very safe. They want to keep it as safe as possible, so it's conservative by nature. Ethereum, on the other hand, they try more stuff. So maybe it will be easier to convince these people than Bitcoin people, maybe.
Were there any other questions for Pierre at this moment? If not, then thank you very much for your presentation. And we will now have a panel which will be hosted by Patrick McCory, who is an assistant professor at the University College London. And if you could just stay in your seats, we're going to quickly set up 4 chairs here, and we'll have the panelists on stage, and then we can get started.
Oh yeah, I need to give it back to you.
Just a quick correction. Patrick, of course, is an assistant professor at King's College London. That was my mistake. Right, so if we could have up on the stage Fisher, you're already here, Mustafa Al-Bassam, and has anybody seen Greg Scullard or Lefteris Kokoris Koya? Sorry. And maybe Lefteris will join us in a second.
Testing, 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 testing.
Sorry, I was thinking. Oh, my voice is back on. Okay.
Sorry, is my wire stuck on the badge?
Hmm?
Thanks. Thanks.
Let me check Twitter.
Okay.
Because Lefteris is on his way back, so I think I told him to be here for a quarter to, so he has 5 minutes. But okay. Good. Let me get my questions back up. Okay, should we begin? I think. Okay, shall I just begin? Yeah, go for it. Does anyone want to volunteer to come up and you can uplift Harris's seat? Anyone from the audience? Oh, come on up. Awesome.
Well done. Round of applause.
Yeah.
Maybe that's another way.
It's not too technical.
No. Oh, hopefully not. Let me move this out of the way. Can we get one more chair for when Lefteris gets here? Because he will get here. I think he's just in one of the museums, being a tourist. Okay, so I'm going to sit over here. So hi, guys. My name is Patrick McCory. We've already been introduced. I think every speaker should have an opportunity just to reintroduce themselves. So I'll just go from this order here.
Okay. Hello, my name is Anais Urlich. I'm the head of research at Eden Block Ventures. So we are an investment and research fund and currently involved with a variety of projects, including ChainSpace, where Mustafa is part of. Yeah.
Yep. So I'm a PhD student. My name is Mustafa, by the way. I'm a PhD student at UCL in London and co-founder at ChainSpace, which they're an investor in. And I'm interested in sharding and on-chain scaling and how to shard verification.
Good afternoon, everybody. For those of you who weren't here yesterday, I'm Greg Scullard, lead developer advocate for Hedera Hashgraph, and we're deploying a public network which is fast, fair, and secure. So that's why I'm here. Thank you.
Hello everyone, my name is Ming Chao Yu. You can just call me Fisher. I am a staff engineer at Dolby Laboratories. So I'm in charge of the research and innovation in distributed and decentralized content creation and delivery. Thank you.
Awesome. So guys, for anyone in the room who wasn't aware, the very first edition of this workshop was actually about off-chain and layer 2 protocols. So the whole point of a layer 2, actually who was at off-chain? Raise your hand if you were there. Some people, okay, this is actually a different audience then, that's even better. Okay, so the whole point of layer 2 is simply to reduce the load on the blockchain. So instead of sending every transaction to the network, you just send the start and the end, and that's it. And that's because these blockchains don't scale. Now the question is, as we've seen over the past 2 days, about these new blockchain and sharding protocols, they propose that they can do 5,000 transactions per second. If you can do that TPS, then was the whole previous workshop a waste of time? You know, do we actually need layer 2? So I'll point at the Mustafa because I see that smile on your face.
Wait, sorry, which protocol did you say was?
Is it layer 2?
Oh, okay,
so was layer 2 a waste of time?
Wait, so you're saying do we need layer 1 if layer 2 could do 1 billion transactions? Is that
No. If layer 1 can do 5,000 transactions per second, do we actually still need layer 2? I mean, do we really need to play Battleship off-chain if we can play it on-chain?
Well, 5,000 transactions per second isn't enough, is it? So we do need layer 2. And even if we did do 1 million transactions per second on layer 1, we still need layer 2 because at the end of the day, no matter how you scale on layer 1, whether you're sharding or bigger blocks, and even if you have fraud proofs, it's still fundamentally on layer 1, you've got a trade-off between decentralization and throughput. And ultimately, like, sure, there's ways to reduce that, for example, by sharding verification, like fraud proofs, but ultimately, this trade-off still exists, and if you take that to an extreme, then you're going to have very little decentralization. So you do need layer 2 scaling, but you do also need layer 1 scaling to support layer 2.
Awesome. Any other comments or? Oh.
So no, we don't. Not with Hashgraph. I guess for the technologies that have been built at layer 1 that have inherent limitations, and I was going to ask a question, maybe it's a naive question, but why are we trying to scale Bitcoin? I thought the point of Bitcoin was that it gets slower over time, and that was its value in some respects. So, but that aside, so we can run 100,000 cryptocurrency transactions per second. So initially, we don't see a need for layer 2 scaling.
But under what network assumptions?
ABFT assumptions.
Yeah, but how much megabits per second do you need to run 100,000 transactions per second?
Sure. So there's a trade-off there in terms of network performance, but we can shard if we need greater than that. But like I said earlier, technologies that are inherently maybe more bottlenecked at the layer 1 potentially needs layer 2 technologies to help them scale. Yeah.
Okay. Any other questions or points?
Okay, so me. I believe it's a combination between the two, layer 2 and layer 1 solutions. And inherently, I don't think they focus on the same problem. Even though they both aim to scale the blockchain, they don't focus on the same problem, and they don't have the same problems in their implementation. So what we can see here, we struggle, for example, with consistency issues between shards. Whereas if you have, for example, a plasma solution, you wouldn't necessarily struggle with consistency issues because it would mostly involve players whom you already know. So in that sense, you would struggle with different issues, and those have to be addressed differently. But at the same time, I believe that layer 2 solutions are at the moment more feasible to deploy on a smaller scale, but ultimately to scale on a big scale and to enhance usability on a wider range, we will need layer 1 solutions.
Mm-hmm. Yeah, and do you have any points? Or?
So I don't know too much about layer 2, but my comment would be I don't think 5,000 transactions per second would be enough to it's the end of our goal. Yeah. So I think in the future, if we look forward, if we implement blockchain for things like Internet of Things, that we might need like millions of transactions per second, perhaps. So yeah. So I think there are still work to do.
Yeah. I mean, I guess for my best opinion as well, is I do layer 2 research. So what's really nice about layer 2 is that we can run an application without ever talking to the network. So you don't really care about network latency at all in terms of like the wider global network. You just care about latency with your peer. So that's one advantage, you know, it's actually much faster for applications.
I also want to say that I think it's not meaningful to talk about purely about transactions per second, because like theoretically speaking, like Bitcoin today, if you just remove the block size limit, it could scale to 1 billion transactions per second.
Yeah.
If you have a terabit internet, if you assume the full nodes have terabit internet connections. The question is, what network resources do you assume the nodes have, and what kind of decentralization and security guarantees do you have?
Yeah, you're getting to my later questions.
Sorry?
You're getting to my later questions.
Oh, cool.
I've got one other question since we have a VC here now, like an investor. So I went, like, a few weeks ago, I went to this dinner in London, and I didn't actually realize they're all like hedge funds. And they were telling me it's basically this year is the year of consensus protocols. All investments are on consensus protocols. So actually, as an investor, what are you more interested in? Like new consensus protocols, new blockchain protocols, or layer 2?
Well, it depends, which is obviously the answer for many questions. But I wouldn't say that, at least us at Edenblock, we are not interested in one over the other. We are interested in the connection between multiple solutions, and we wouldn't focus solely on consensus protocols, because they are just also means to an end. So what we focus on, for example, right now is also usability. We have a bunch of blockchain applications, right?
Yeah.
And we try to optimize those, but at the same time, most use cases won't be possible because we either don't have the technical solutions or because there is just no network effect happening which are required for those solutions.
Yeah.
So ultimately, we focus on usability as well, which is probably on the other end, yeah.
I think that's really important. In fact, one of the cheeky comments I've been giving all week is that as a community, we probably focus too much on infrastructure and not enough use cases. Do you guys agree with that, actually? Are we focusing too much on infrastructure and not enough about usability?
I think there's plenty of use cases, it's just that the infrastructure doesn't support it, right?
Yeah.
Yeah.
Any other comments? Or?
Well, I guess adoption at the end of the day will depend on use cases. We can come up with the best technology in the world, but unless it has a use, unless there is a problem to solve with our solutions, then there's nothing to do, right?
Okay. Anything else, or you're all happy?
Yeah, I think I'll just agree with you guys.
Okay. Well, one thing I'm going to mention as well, so this is sort of gets into the new blockchain and consensus protocol world. So what's really cool about Nakamoto consensus and Bitcoin is the very low overhead. You know, I receive a block, I hash it, I look at the puzzle, I say, yep, that's a valid block, and then I accept it. But as everyone here has seen, for new sharding protocols and for new blockchain protocols, there's a significant more overhead. They actually realize if a block is valid. So for example, we could think of like OmniLedger, for example, and we look at the committees and we say, why is this person in a committee? To do that, you have to validate the transcript to say, okay, you know, there was this random beacon, they did the shuffle or whatever, and now he's in the committee. So that's a significant overhead for these new protocols. So my question is, you know, if we have this overhead, is that going to have like practical implications in terms of real world use?
So what kind of overhead are you talking about? Do you mean like...
So it's like storage, bandwidth, you know, you've got to send this protocol transcript
communication overhead?
Yeah, communication, storage, block size. I mean, even as a community, like over the past years, in the Bitcoin world, you know, they argued about 1 megabyte block, 2 megabyte blocks. But actually, if some of these protocols are, you know, deployed, it could be like 10 megabytes just to do the consensus protocol. So is this going to have implications for us?
Do you mean, are you talking about, like, for example, the messaging complexity in BFT?
It could
or
be.
like
That'd be one aspect. Or just even as an external observer, I download the block, and I have to convince myself why this block is valid. So the overhead there is a bit more in terms of the protocol transcript.
But why is that bigger in sharding, in your opinion?
I mean, if you think about sharding, you know, I join a shard, there's these committee members, and they're being reshuffled from time to time. I have to see why they're being reshuffled. So I should probably validate that.
Yeah. I mean, I think it depends on, like, for example, in theory, you don't have to have a lot of that overhead. Like, if you look at a lot of sharding protocols, the consensus algorithms use consensus algorithms with higher overheads. Like BFT has a higher overhead than Nakamoto consensus. Like Nakamoto consensus has 0.1 message complexity for you to convince yourself that a block is part of the consensus. But with PBFT, for example, which is what systems like OmniLedger or ChainSpace use, there's ON message complexity to convince yourself that a message is valid. But in theory, you could just replace that with Nakamoto consensus. But the reason why some of these systems use consensus protocols with higher overhead is to get faster finality. And in systems like sharding, that's essential, because if you have one shard that has a fork or has a reorganization, then potentially every other shard has to have a reorganization as well. So you have this cascading effect that you want to minimize. But I mean, I don't necessarily think that overhead has to exist. Like if you look at systems like Casper FFG, it achieves finality without that overhead. So I'm not necessarily sure that overhead is inherent to sharding, and I think there's ways to avoid that. Like one of the overheads could potentially, for example, be having to have lots of signatures on the block, for example, but that could be avoided with schemes like BLS signatures.
I guess I'm more of an engineer, and I look at it as a trade-off. If there's a benefit to the overheads, and that benefit is positive, then is it such an issue?
Yeah, I guess that's the price we pay for a trustless system. So you have to pay for it. The problem is how to minimize it.
Yeah. I mean, I think even though you do have might have an overhead, it's still the case that if you use sharding, it's linear scalability. So I think the fact that the scalability is linear kind of overshadows the fact that it has higher overhead, because ultimately you still get higher scalability even though the overhead might be higher.
Okay, I can move on to another question as well. So there's two categories of consensus protocols. You have like fork avoidance protocols, which is pretty much like BPFT. We avoid forks like the plague. We should never fork. That should never happen. Nakamoto consensus was the first protocol really to tolerate forks. If there's a fork, we get eventual consistency, and we sort of says eventually agree. What do you guys think are the trade-offs there compared to having this eventual consistency versus instant finality? Because actually what's happening now is that, as you mentioned with sharding, we're now moving back to the instant finality world. And even with stuff like Thunderella, what you have is instant finality at the top, but eventual consistency is the lower layer. Do you guys have any thoughts on that?
So I guess it depends on what you need your consensus finality for. If you're we often use I go to a bar and I buy a beer with some token, or I go and buy a coffee in a coffee shop. If the coffee shop owner wants to know that you're actually paying for something, it needs to be pretty instant, right? We have that guarantee today with many fiat payment systems such as Visa and so on. So in those use cases, I guess you need that instant finality. You need to know that this can't be reversed. This can never change. And in other cases, then maybe waiting a few hours or a few minutes, or trusting that X% finality is a good enough risk to take. In some use cases, may be perfectly okay. I mean, Lehman, our CTO and chief scientist, is a mathematician, and anything other than 100% is just not good enough. So as far as he's concerned, it's 100% finality or nothing. 99% still has, or even 99.9% still has a risk of being undone, however difficult that is. I have to favor 100%. But I guess it, again, depends on use cases. Horses for courses.
Any other comments or...
I mean, I think sometimes the desire for instant finality is overrated. I don't really think. I think I'm sometimes misplaced. If the argument is because you need to make sure that your payment is accepted straight away, I don't think that's a strong argument for having instant finality, because, in theory, I mean, in Bitcoin right now, a lot of people make this argument oh yeah, you have to wait 6 confirmations for to wait for to buy a coffee or something like that. But at the end of the day, you don't really you don't need any confirmations at all to buy a coffee because it's so low risk that a double spend attack is unlikely. But in some cases, you do need instant finality, like when it comes to sharding. But in theory, Bitcoin, Nakamoto consensus does, in my opinion, has similar finality guarantees to traditional consensus protocols. It just takes longer to achieve that finality. So it's not that a lot of people say Nakamoto consensus has no finality, but it actually has the same kind of level of finality as BFT protocols. It just takes longer to get there because you need to wait a bunch of blocks. And that's why sometimes you do need that instant finality. Yeah.
Okay. Any other comments?
So I would agree it depends on a use case.
Yeah.
I also believe that if it's a small transaction or depending on the transaction you make, right? Depending on the use case. If it's financial transaction, then obviously finality is more welcome than partial finality. But at the same time, obviously, as systems become more complex, you would want to have instant finality because just partial finality would probably make sharding, etc., more complicated.
Yep.
I assume.
Yeah.
Okay. Anything else, or okay? Okay. So another question before I move on to the audience and let them have a turn at grilling you guys. So normally we live in our own little bubble, and we all love our own protocols. But if you had to name another protocol that you really liked, what would it be? And potentially, what reason? Why do you like it?
What would I call the protocol?
Another protocol that you're not involved in. So maybe I could say I like chain space because I'm not involved in it, for example. Yeah. So I'll give you guys a second to think about it.
I'll tell you right away.
Yeah.
Bitcoin.
Okay, well that's cheating.
We wouldn't be here without it.
That's fair.
Yeah, I agree with you. I think Nakamoto consensus is underrated.
Okay, let me rephrase this question. A protocol that's not built yet or being built. You can go first if you want, because you're in the world of investing. You're not allowed to say chain space. Conflict of interest.
No, chain space. They're one of our favorites, but I would say there's a protocol called TODA protocol, and
TOTLE.
TODA.
Oh, DA. Okay.
And what they are doing is pretty interesting as well. So they are currently being built. They are not built yet. It's basically a huge binary tree, as described before as well, where you can store any information you want. And the consensus works different. It works basically up the tree rather than as a DAG.
Okay.
Yeah.
Awesome. You can go next, Mustafa.
I'm kind of looking forward to see how Plasma plays out, because I think it's such a complicated protocol if you implement it fully. When you try to implement mass withdrawals and mass exits, it's kind of like sharding but non-uniform. So I'm kind of interested to see how that plays out.
Okay.
Yeah, I tend to agree. Be curious to see how EOS and Ethereum play out over the next few years.
Yeah. I think EOS is actually quite... I'm sorry, I'm just interrupting now. I think EOS is quite interesting in the world. Apart from all the drama that's associated with it. If you look at classical consensus, there's no incentives at all. You just hire these nodes and they do the job for you. Then you get Nakamoto consensus, and this is more like a free market in the sense that I buy hardware, you buy hardware, and now we just compete and we try to outdo each other. But then you have this DPoS, which is more like a democracy or government, like liquid democracy. I elect people and then they vote on my behalf. And as we've seen, that comes with lots of problems that are always associated with democracy. So yeah, I think it's going to be quite an interesting, if it works. I guess.
Yes, I think my favorite, apart from our own Polyshark, is Omni Ledger.
Okay.
Yeah, so the first glance when I look at the paper, I feel it's a very clean design. Yeah, and also its different components. It's also interesting, such as the random hunt thing. So I think Omni Ledger is my favorite. Okay,
that's awesome then. Sure. Do you want to jump up, Lefteris, by the way? We can get you one more seat. Yeah. Go. Grab him a seat. I want to get Lefteris up here. Yeah. Okay, so we'll start taking questions from the audience after we get that chair. Awesome. Come on up, Lefteris. Yep. So I can ask you the same question. What's your favorite protocol except for OmniLedger? Oh.
Yeah, so I think I really like what they do at UCL, like with George, both like chain space and the Blockmania was very interesting of like how they get a reliable broadcast primitive that's simpler than consensus, and then play around a bit, and you magically get consensus after it. And I found it very interesting.
That's awesome. Yeah. Okay. So yeah, I can move on to the audience. Does the audience have any questions? I'm sure. Yep. There you go.
I have been hunted by this question since I got this invitation of coming here. What exactly is layer 1 and what exactly is layer 2?
Oh, well, I was at a Dijkstoel last week, and we had this whole argument about it. Layer 1's actually several layers. I'll let you guys answer, though. I don't want to jump in the panel. Who would like to take this?
Well, philosophically, I think it's a bit of a philosophical question. Like, I think the way I see, I mean, the way that many people see it, and what I'm going to say is not original, but like, they kind of like if you imagine the blockchain as a kind of like a decentralized court system, so like it's kind of like a verifiable international court system. Everyone sees the result, and it's like the idea is, well, you don't need every single transaction to be verified or go through a court, right? So you just need disputes to go through the court. So the idea of layer 2 is that you just, if you have a mutual contract with someone, you just sort that out between yourselves, and only if there's a dispute, you go to the main chain, i.e. the court. Sorry, I guess that's quite a
very quick follow-up question.
Yeah.
Then why sharding is considered as layer 1?
I think Lefteris has a good answer to this.
Yeah, so
we had
to answer, like, I agree that sharding could be like layer 1.5, let's say. Like,
I think,
like for me, layer 1 would be a global state, right? Everyone sees it, everyone validates it, and then you have layer 2, where it's a very specific substate that you get 3 nodes, whoever cares about it, and they validate that, and then you have sharding, which is kind of in between. Like, not everyone sees it, but it's actually still secure by design and still public. So it's somewhere in between for me.
Yeah.
So I think, I would see sharding as layer 1. The reason for sharding being layer 1 is because every single node needs to be sure in some way or another that the on-chain state of every shard is valid, whether that be directly by verifying it themselves or indirectly through fraud proofs. They need some assurances that the on-chain data is valid. Otherwise, the whole state of the system becomes corrupted. I think what is more like layer 1.5 is systems like Plasma. So like the idea of Plasma is that it's kind of like sharding / sidechains, but it's like anyone can create their own sidechain that feeds back into the main chain, but only the participants in that sidechain have to actually care about that sidechain. So it's kind of a mix between layer 1 and 2 anyway, because not everyone has to verify the state of every sidechain. But straight sharding is layer 1 because everyone cares about the validity of the state.
If I may ask the last question then. So then you think that the difference between layer 1 and layer 2 is the security then? So basically, if you think it is as secure as it is on-chain, then it should be layer 1. Otherwise, if it is rely on some other assumptions.
I don't think it's that. I think the way I normally envision layer 1 is that layer 1 is a consensus protocol. If it breaks down, tough luck. Game over.
No, but you can have consensus protocols in Plasma as well, no?
No, exactly. So layer 2 is another consensus protocol. And if this breaks down, it has this root of trust, this highly reliable underlying blockchain that will always back it up. So in Plasma, if the operator disappears, we always get our coins out. If it's a state channel and we're playing like Battleship or chess, the channel breaks down, we just go back down to the base consensus layer. So there's 2 consensus layers going on. One's a very small subset.
So then what divides layer 1 and layer 2 is that's whether invalid transaction will break the whole system.
Not invalid, it's just the consensus protocol breaks down.
Okay.
Maybe you hit the security threshold. I mean, we all have different opinions. That's how I see it. And actually trying to get a consensus on that would be quite useful.
I also don't know. I just want someone.
Yeah.
Excellent. Was there a question here?
Just to add on the clarification between L1 and L2. So if it depends on its own mechanisms for maintaining security, liveness, safety, whatever, it's layer 1. if anything that happens, if like your system is compromised for whatever reason, and to resolve your disputes you need to go to another chain or something, that's layer 2. And this is like what happens with Plasma or channels. But sidechains are not layer 2 in my dictionary.
I would say non-custodial sidechains.
Yes, that's what Plasma is. But for sidechains, for example, they're not layer 2 in my opinion, because if the sidechain consensus is compromised, the sidechain is done.
So you think it's layer 1?
Yes. I consider sidechains to be like, there's no like layer 1 and 2, they're on the same layer, and they just are for interoperability.
Well, depends how they are structured, no?
There's no start, they're on the same level, that's what I'm saying.
Well, I don't think they're entirely in the same level, because not everyone who's validating the main chain needs to care about the side chains.
Yes.
I think what he means is that something like RSK or Liquid, if the federation's corrupt or the consensus protocol breaks down, your coins are stuck. There's no way to return back to layer 1.
Mm-hmm. No, but in Plasma, you don't...
No, Plasma's non-custodial. Exactly.
Okay, right.
That's the distinction. So custodial sidechains and non-custodial sidechains.
So it depends, right?
Yeah, it depends on the security requirement.
Yeah, but what I'm saying is that there's a different security model in the Plasma versus sidechains.
But I don't think it's a security model that necessarily makes it layer 1 or 2. Like Plasma, from the main chain, Plasma looks like a custodial sidechain from a technical perspective, but it just has higher security than a custodial sidechain because of the ability to do a mass exit if there's no liveness, in my opinion. Yeah.
That is accurate.
Sorry?
That is accurate.
Yeah.
Any other questions?
Excellent. Roman, did you have a question?
Maybe even not a question, maybe join to discussion a little bit, if you don't mind. So today I heard, yesterday and today I heard that several people mentioned finality of Ethereum Casper. It's a very convenient marketing term, but it's not finality in the meaning of BFT protocols like PBFT, if you're speaking about a leader-based protocol, or about Honey Badger or Hashgraph. These protocols really provide finality, but Ethereum Casper provides finality only in terms of honest 2/3 of participated stake. So, for example, if we have 1% of locked stake for the validators and 2/3 of them, so less than 1% is honest, then we really have finality. But if we can involve another 3% of the whole stake of Ethereum and to participate as the validators, there are no finality at all. So there are some different...
Casper's more like economic finality in the sense that you have to compromise your saying 2/3 or 1/3 of the coins to reverse history. So it's economic in that sense. You're only going to do it if you don't want to lose the money.
Yes, but we need to understand that it's not for full stake, but for some small portion of stakes that it's currently locked. So it was an interesting discussion between Vitalik Buterin on Reddit, and it was explained in details. Okay.
Mm-hmm.
Thank you.
Any other comments on that? Okay.
Excellent. Were there any further questions from the audience for the panel? If not, then I'd just like to thank you all. That was really, really fun to watch. And let's have a round of applause for our panelists. In particular, Anais for stepping up. That was very brave of you. So thank you. Thank you, Patrick, as well. So that's it for our event. In closing, I just wanted to thank all of our speakers across the 2 days. I think we've had some really interesting talks. It's been great to hear from academics who are doing the cutting-edge research to get an idea of the state of these scaling proposals and what we might be looking at in the near future. I'd also like to thank the audience. We've had some really good discussions. We've had some challenging questions, and it's been really fun to see practitioners and other enthusiasts respond to the presentations of our academics. So thank you all for joining us. Finally, I'd like to thank Binary District and Research Institute for organizing this excellent event. I've got more good news. There is another master workshop coming up. It's going to be in London. It's in May, and it's going to cover zero-knowledge proofs. So I'm very excited about attending that as well. Yeah, that's all I have to say. We've set a high bar for the event in London, so be sure to come to that. And speaking of bars, I think we all deserve a drink. So let's have a final round of applause, and thank you all very much.
Awesome.